Okay, the third illustrative example that we are going to be looking at deals with the in-plane flexure and shear design of a reinforced masonry wall. So, this is specific to component design that we will be looking at, particularly for in-plane shear, in-plane flexure and in-plane shear. So, let us consider a shear wall of dimensions 4.3 meters in length and 3 meters in height. It is constructed with the hollow concrete masonry units of thickness 200 millimeters. We are designing the wall for in-plane flexure and shear. The lateral seismic force considered here is 38 kilonewtons. Now, this seismic force corresponds to a reinforced masonry wall, and of course, it depends on the R factor that has been used to arrive at the seismic force corresponding to this level in the wall. So, this is a lateral seismic force which we can use for a reinforced masonry wall. If you were to design this as an unreinforced masonry wall, or check if an unreinforced masonry wall is feasible, then the lateral seismic force should be different, because the R factor that you would use for an unreinforced masonry typology will be different. So, what are the aspects to be determined? The in-plane flexure reinforcement and the in-plane shear reinforcement. The data that is available with us, there is a live load acting on this wall. You can assume that these calculations have been made on a building system, and then the live load acting on the wall is provided to us. A superimposed load of 32 kilonewtons also acts on the wall, and the lateral seismic force corresponding to the reinforced masonry typology will work out to 38 kilonewton in this wall. To estimate the self weight, the dead load due to the self weight, the unit weight of masonry can be considered to be 20 kilonewton per meter cube, and the prism strength of masonry is 8 megapascals. The permissible stress for steel, considering HYST bars, is 230 MPa, and hollow block construction, the width of the bed joint mortar that we will be considering in our calculations is 60 mm. So, we are basically looking at 30 plus 30, which is the shaded portion that you can see on your slide. So, this is the width of the bedded mortar, 30 plus 30, that we are going to be considering in the calculations. And that is a typical assumption. The region, the web is typically not mortared. For ease of construction, that portion is normally not mortared, and even if it is mortared, you can neglect the contribution of that area in a hollow block construction. Part of the cavities may be filled with your grout, and part may not be. So, let me come to the load cases, calculations of the load cases and the combinations thereof. So, self weight of the wall is one of the dead loads that you have to consider. This is a hollow block construction. Let us assume that 50% of the blocks are retained as hollow. So, 20 kilonewton per meter cube into the width of the wall 0.2 meters, 50% considered to be hollow, and the total length of the wall and height of the wall 4.3 and 3 meters respectively. We also have a superimposed load acting on the wall, 32 kilonewtons. Therefore, the total dead load is 32 plus 25.8 kilonewtons, which is 57.8 kilonewtons here, and there is a live load or an imposed load of 15 kilonewtons acting on the wall. We are looking at seismic design, and therefore, we are going to be looking at an earthquake plus gravity load combination, and under this combination increase in permissible stresses is permitted. So, you should be looking at how permissible stresses can be increased. Either you increase the permissible stresses in your calculations by 33% in this earthquake plus gravity load combinations, or you have the possibility of taking that to the other side of the equation and reduce your loads to 75% and continue to use 100% of the permissible stress, not 133%. So, that is more convenient to do, because you can uniformly apply this to all your loads and load cases, including the combinations. So, we will reduce the load to 75% in our calculations to account for the increase in permissible stresses which is permitted due to the combination. What are the load cases we can consider? Okay. Typically, these are the two load cases that we should consider. One is a situation where you have the dead load, you have the beneficial effect of the live load, and you have the earthquake load. So, it is the gravity plus earthquake combination, including the positive effect of live load, and we are taking 75% of the load because of the statement that I made earlier. So, 0.75 into dead load plus live load plus earthquake load is our first load case, and a second load case is primarily to account for effects where there could be decompression to an extent in the structure, and therefore, we look at a reduced dead load and we do not consider the live load. So, the load case is 0.9 times the dead load plus 100% of the earthquake load. In this case, considering 75% of the total load, we have the load case as 0.67 dead load plus 0.75 earthquake load. Okay. At this stage, I just would like to point out that these two load cases that we are looking at are appropriate for a working stress approach. However, if you were to consult IS 1893 Part 1 2016 or the 2016 version of the National Building Code, the load cases stated there pertain to the limit state approach, where you will see that the factors prescribed for the load combinations, load cases in the load combinations is coming from a limit state approach. For example, you are required to do checks for load combinations of 1.2 times dead load plus live load plus or minus the earthquake load, 1.5 times the dead load plus the earthquake load, or a case of decompression happening where you have 0.9 dead load plus 1.5 times plus 1.5 times the earthquake load. So, this is not applicable for the working stress approach that we use for design of reinforced masonry and design of masonry as such. So, word of caution that these will penalize the design if you were to apply to a working stress approach. For the earthquake load, we will take 75% again of the earthquake load. So, the shear force into the height will give us the overturning moment. 0.75 into 38 kilonewtons was what was prescribed for the design of the wall, prescribed lateral force for the design of the wall, height 3, and therefore, we are looking at a moment of an overturning moment of 85.5 kilonewton meter. What are the axial load cases? That was the earthquake load. We had the overturning moment from the earthquake load, and now for the axial loads, we had two cases. The first case was looking at 75% of dead load plus live load, and therefore, our case P1 would give us about 54.6 kilonewtons, 75% of the dead load and live load estimated. That is your case 1, we call it P1, case 2 with the reduction in the dead load. So, 67% of DL dead load is what we will consider. This works out to about 38.7 to 6 kilonewton. So, we have two cases that we must look at in design. I will take up one of the cases and we will go into the details, and one should be looking at both the cases to see which would give you the worst case scenario as far as the design is concerned. Some aspects of the geometry and permissible stresses that we will be requiring. The net bedded area, we just talked about this, 60 millimeters into the length of the wall 4300 millimeters. The net bedded area is 0.258 Newton millimeter square. We need to estimate the second moment of area, and the second moment of area is estimated considering the geometry of these two strips that are sitting about the center line of the wall itself. So, the second moment of area is estimated to 0.3994 meter to the power 4. We need effective depth calculation for in plane flexure. So, we are really looking at, let us assume steel reinforcement is going to be placed at the two voids that are present in a block, and therefore, the centroid of the reinforcement can be considered to be in the middle of the two reinforcement bars, and therefore, that is 1/2 of the block, and therefore, we can assume that the effective depth is calculated from extreme compression fiber to the centroid of the steel reinforcement, and that is 200 mm from the edge, and therefore, the effective depth is taken as 4100 millimeters. Of course, if the steel reinforcement is going to be placed in many more cells, then you will have to adequately come back and check, come back and make alterations to the effective depth calculation. The permissible compressive stress estimated as 25%, 1/4 of the compressive strength of masonry, which was 8 megapascals. So, Fa is 2 megapascals, Fb, because of the strain gradient effect, Fb is increased, you have 1.25 times Fa, that would be 2.5 MPa, and Fs, as stated earlier, is 230 MPa. Modulus of elasticity is required primarily to make the estimation of N, the modular ratio. So, Em is 550 times Fm, and that is 4400 MPa. So, the modular ratio, modulus of elasticity of steel, 2 into 10 power 5 MPa divided by 4400 MPa is 45.45, which we will use in our calculations. Okay. So, let us look at the design, the iterative approach that we talked about. There are two procedures, and it is up to the designer to choose the approach he or she would like to use. Both are iterative procedures, and there can be other methods also that one can use. Basically, the fundamental requirements are almost the same. So, we will look at procedure 1. In procedure 1, we were first making an assumption that compression controls, and then check whether that assumption is true for the depth of neutral axis that is estimated, and then if not, make changes to the way the neutral axis depth is calculated, and then arriving at the area of steel that is required. So, under the action of the external moment and the load, the total length of the wall is Lw. The neutral axis, the effective depth is Lw minus d dash, which is d effective. So, d dash is the distance to the centroid of the steel reinforcement, that is where your tension resultant is acting, and then you have the triangular distribution of compressive stresses, and C is the resultant in compression. The length of the compressed zone, which is the depth of the neutral axis, Kd, is what we need to estimate. We also require J, which is Jd, which is 1 minus Kd as well in calculations of respective stresses. So, let us assume in the first instant that the masonry compression controls and calculate the compressive force in the masonry. Fb, because it is flexural compression now, into B, which is the width of the wall, width of the net bedded area is what we use here, B, into Kd, d being the effective depth that we calculated, by 2, and therefore, Fp is 2.5 as estimated earlier. The bedded width 60 mm, K is unknown and effective depth is 4.1. So, we have an expression for the compressive force in K, taking the moments to be equal to 0, taking the sum of moments is equal to 0, we can write down the quadratic expression in K. Basically, we are looking at the compressive force minus the effect of the axial force and the eccentricity P into Lw by 2 minus d dash minus m should be equal to 0, and therefore, we have the quadratic. You can solve the quadratic. This is a single K. You have 420.25 K square minus 1260.75 K minus 191.970. Solve the expression for K and we get a value of 0.16 for K. Now, with that you can go back and estimate the compressive force, and since we know that the tensile force is going to be by equilibrium C minus P, we get an estimate for the tensile force. Now, with that let us check the stress in steel, and the stress in steel because of the stress in steel is estimated because now as the compression controls we have the stress in masonry equal to Fb, and therefore, from similar triangles and compatibility we can estimate what the stress in steel is, but this stress in steel works out to be much higher than the permissible stress in steel, which is 230 MPa. Now, this implies that the assumption that masonry compression controls is wrong, and therefore, the estimate of K is wrong. So, we need to go back and look at a situation where the stress in steel is governing and estimate what is the corresponding K, and then estimate the compressive stress in masonry. So, to follow on to the next step, we assume that tension controls, so the steel controls, and we have to make now an estimate of the effective area of steel. We use the effective area of steel to then check if we are satisfying the requirements that the stress in steel is less than the permissible stress, and whether the stress in masonry is less than the permissible stress in masonry. So, AS effective is estimated as AS plus P by Fs. We are taking into account the effect of the tension that is occurring due to the eccentricity caused by the overturning moment. So, which therefore can be estimated as a sum of tension plus the axial load divided by Fs as a first estimate of the AS effective. So, tensile force that we calculated in the previous step plus P divided by Fs could be a starting point. So, we get an estimate of T plus P as 49.5 kilonewtons divided by Fs 230 MPa, and AS effective is of the order of 215 millimeter square, from which the percentage of steel is estimated, and with the percentage of steel rho effective estimated, we can try and we estimate K from the quadratic expression, and an estimate of K is derived, and an estimate of J as 1 minus K by 3 is also derived. So, we will have to now look at whether with these estimates do we satisfy the requirements that tension controls and masonry stress is within permissible stress. So, let us estimate the steel stress using this using these estimates of K and J as M prime by AS effective into J into D, and this M prime is nothing but the external moment plus the additional overturning moment that is coming because of the eccentricity of the axial force due to the tension occurring in the cross section and a non-uniform distribution of compression. So, that is P into Lw by 2, Lw is the total length of the wall minus d dash, which is the distance to the centroid of the steel reinforcement from the edge, which gives us the additional moment to be considered along with m the external moment itself, and this totally works out to about 191.97. We use it in the previous expression m dash divided by 215.25, which is As effective that we calculated in the previous step, the value of J that we have estimated now, and the depth of the effective depth of the wall. This gives us an estimate of the steel stress, and the steel stress is in this case 228.15 MPa, which is less than the Fs, or the permissible stress in steel. So, this satisfies the requirement. Now, we can basically use two number of 12 mm diameter bars to achieve this As effective here, which is 215.25 millimeter square. Of course, the estimate of As effective was an initial estimate. We can revise that. Basically, if you are going to choose for As effective two numbers of diameter 12 bars, then the area of steel is slightly more. So, it should not matter too much in this particular case. You can see that the corresponding stress in steel is 217.1 MPa and still satisfies the condition that Fs is less than the permissible tensile stress in steel. However, one must check if there are changes in the number of bars required. One must check if there is an update of D dash that is required, and then come back and correct the calculations in this at this stage. The masonry stress is then estimated. Fm has to be estimated, and Fm can be estimated from the similar triangles from the state of stress in the steel, and this works out to in the case that we are looking at 0.4 MPa, and this is less than Fb, which is 2.5 MPa, and therefore all requirements have been satisfied in this particular stage. Okay, so we are looking at two numbers of 12 mm diameter bars that are placed in the extreme edges, considering two directions. Given the symmetry of the structure, we did only one direction, but then it is true for both the directions, and therefore we are looking at two bars of 12 mm diameter that will be placed in the extreme cell on the left and the right ends of the wall of length 4.3 meters. Okay. Now, as far as the shear design is concerned, how do we go about the shear design? So, the flexural design was taken care of in the previous slides. The shear force that we are talking of is lateral force of 38 kilonewton, but reduced to 75%, and therefore we are looking at 28.5 kilonewton as the shear force. Let us estimate first the actual shear stress that the wall is subjected to because of this level of lateral loading. So, the shear stress Fv is estimated as 0.75 into V, which is what we did in the first stage, divided by width of the bed joint mortar multiplied by D, the effective depth. So, we make an estimate of the actual shear stress, which is about 0.11 MPa. Now, if you remember from the considerations that the code makes in terms of what should be the allowable shear stress and the maximum value of the allowable shear stress for different conditions without and with web shear reinforcement affected primarily by the aspect ratio of the wall, or the m by Vd ratio of the wall. We need to choose what the Fv, what the allowable shear stress and the maximum allowable shear stress are. So, in this case, we could, the level of shear stress is low. We could choose to go with either with or without web shear reinforcement and look at the estimate of m by Vd first, and then the Fv and Fv max that we must consider. with and without web shear reinforcement. So, let us first estimate M by Vd. In this case we are looking at 114, which is the total moment, divided by 38 kilonewton, which is the shear force, into 4.1 the effective depth, and the value of M by Vd is 0.73, which is less than 1. This is a rather squat wall. It is 4.3 meters in length, and hence we expect the response, lateral load response of this wall to be basically governed by shear deformations. So, in this particular case, if we are going to be providing web shear reinforcement, the permissible shear stress is calculated as 1/24 of 4 minus M by Vd, the ratio that we estimated just now, multiplied by the square root of Fm, which is how the masonry compressive strength comes in as a parameter that influences the shear strength. So, this is estimated as 0.385 MPa. It is limited by Fe max as estimated here as 0.454 MPa. However, our masonry shear stress is 0.1, the order of 0.1 MPa, and therefore, we are well within the allowable shear stress or the maximum allowable shear stress. If we were not going to be providing web shear reinforcement, we would still be okay. It would be 1/36 of 4 minus M by Vd ratio into square root of F prime M, and even here the allowable stress is 0.257. However, our actual shear stress is much lesser, which means that the unreinforced the wall without providing web shear reinforcement itself is adequate to take care of the shear that the wall is being subjected to. However, let us just look at the case where if we were to provide web shear reinforcement for wall type C, whether the web shear reinforcement that we provide satisfies the requirements of detailing. So, I am providing web shear reinforcement. Now, we basically assume a spacing S. The maximum spacing of shear reinforcement should not be greater than 0.5 times the effective depth or 1.2 meters, and we take the lesser of the two. So, we can check what the minimum shear steel that we are supposed to provide is, assuming a spacing of 1 meter or 1000 millimeters. The minimum area of minimum shear steel works out to be rather low. So, Vs, where V is 28.5 kilonewtons as estimated earlier, Fs is again 230 MPa, and the effective depth is used for calculating the value of AV minimum. Now, the requirements on spacing, the maximum spacing of the horizontal and vertical reinforcement that we must check has to be the lesser of these three values: total length of the wall by 3, total height of the wall by 3, or 1.2 meters. The lesser of the three has to be considered. In this case, length of the wall is 4.3 meters and height of the wall is 3 meters, and therefore, h by 3 would govern, 1 meter would govern, and that is the maximum spacing, and that is why in this calculation I had used 1 meter as the spacing for the calculation. Let us assume we are providing 8 mm diameter bars at 1 meter spacing, and if you are providing 8 mm diameter bars at 1 meter spacing, the percentage of steel then becomes 50.26 would be the area of one 8 mm diameter bar divided by 1 meter spacing. So, that is 1000 by the width of the wall, which is 200 into 100, and gives us about 0.025%. Is that okay? Now, assuming that we are providing web shear reinforcement, is the amount of web shear reinforcement provided adequate for a reinforced masonry wall type C? So, if you remember the prescriptions for wall type C, we need to provide uniform reinforcement in both horizontal and vertical directions. We need to ensure that the sum of the reinforcement in both the directions is at least 0.2% of the gross area of the wall cross section. minimum reinforcement area in each direction should not be less than 0.07 of the gross cross sectional area. So, that is something that will get violated, because earlier we saw 0.025% is what we get by providing 8 mm bars at 1 meter spacing, and then in the horizontal and the vertical directions together we must get at least 0.2%. So, it is important to go and check if we satisfy these requirements. So, providing web shear reinforcement, we assumed we made the calculation for an assumed spacing of 1 meter. We checked that the 1 meter would not be adequate, and therefore, with the 1 meter spacing we get in the horizontal direction, we get the percentage of steel as 0.025%. Therefore, we assume 10 mm diameter bars at 500 mm spacing, and the percentage of steel in the horizontal direction is then estimated as area of one steel bar divided by 500 mm spacing, width of 200 mm into 100, and we get about 0.078%, which is greater than the 7% that is required. Now, percentage of steel in the vertical direction rho is 78.54 divided by, assuming we provide steel reinforcement in alternate blocks with one block of height 150, each block of height 150 mm. So, in the vertical direction, if you are looking at how many bars have to be provided, so this is alternate blocks, so that is 2 into 150, we get about 0.13% for a 10 mm bar that is going to be provided at alternate courses. So, this is again greater than 0.07%. You have another requirement that the horizontal and the vertical, the steel in the vertical direction should be 3 times that of the horizontal steel, and therefore, you would have to probably reduce this to 150 and check that the additional requirement of vertical steel being 3 times that of the horizontal steel is also taken care, and the sum of the reinforcement in both the directions would then be 0.078. The sum of the reinforcement in both the directions would be 0.078 plus 0.131, and therefore, 0.209, which is 0.2 greater than 0.2%, which was what was one of the requirements. So, therefore, we actually have looked at the shear design aspect. This wall could actually be left as left without providing web shear reinforcement, but if you were to provide web shear reinforcement, these are the checks that need to be carried out to ensure that minimum steel for a certain type A, B or C is taken care of. Okay. With that, let me talk of one last aspect, which is peculiar to perforated shear walls. In the previous case, we looked at one blank wall which was 4.3 meters in length, and if we were to consider that to be a multi-storied structure, you would have the shear wall design carried out in a very similar manner as you saw in illustrative example 3. But if you were to look at a perforated reinforced masonry shear wall, the one item that would change, and you need to adequately consider that in your calculations, is the overturning moment causes different axial forces in piers. There is a change in the axial force due to the earthquake force and the overturning moment caused by the earthquake force, and that has to be accounted for in your calculations. So, if you were to look at the gravity forces, the gravity forces would come from the dead load, from the live load, and from the earthquake force because of the overturning moment. So, the additional axial force from the overturning moment, which could be tensile in nature or compressive in nature, depending on the direction of the earthquake and depending on the position of the wall with respect to the overall geometry of the structure that you are considering has to be in addition taken into account. So, the distribution of the overturning moments to piers as axial forces has to be considered. So, you have this additional axial force coming from the earthquake forces Pe of the different walls. If you have to calculate that for the different walls. So, basically how can you calculate that and where is it coming from? The lateral force acting on the perforated shear wall which composes the overall building is actually going to cause a situation of additional compression in the extreme piers and a situation of tension in the one on the left end, considering that the earthquake force is acting from left to right. The typically the in this case we have 3 piers. The pier in the middle, if it is aligned with the center line of the overall building plan, then would see minimal alteration in the axial force because of the overturning moments, or the axial force corresponding to the overturning moment would be close to 0. However, that depends on the geometry, but what we should be careful about is how are these 2 piers in this wall which is made out of 3 piers, how is the axial force due to the overturning moment and what is the quantum in the extreme piers. So, we are interested in estimating what is the neutral axis of this cross section. The wall made out of 3 different piers, you have pier 1, pier 2 and pier 3, and therefore, we will be able to estimate the axial force corresponding to each of these piers, in this case pier 1, pier 2 and pier 3, as the area of cross section of each pier, which is Ai, into Yb of I, which is nothing but the distance between the centroid of each of the piers that is being considered to the neutral axis, distance from the centroid to the neutral axis of each of these piers, which is Yb of I, divided by the sum of the moment of inertia of the total moment of inertia about the neutral axis, multiplied by the overturning moment. So, the effect is due to the overturning moment into the respective areas into the distance between the centroid of that cross section from the neutral axis divided by the moment of inertia or the second moment of area of the cross section with respect to the neutral axis. So, this additional component of axial force needs to be considered, and as you can see, depending on the level of lateral force, the extreme piers can actually have a beneficial effect due to additional precompression or be in a disadvantageous situation due to the uplift or even be subjected to tension. And since you know that the shear capacity is directly dependent on the level of precompression, you can have very different situations in the piers, and therefore, design has to adequately consider this particular aspect. And if there are significant deviation from symmetry in the plan, then that is again going to be a cause for concern in the actual design forces to each of the piers.